Okay. Section 2.3 is about reactants colliding during chemical reactions. And let's take a look at the warm-up. What they've put in each of these boxes is reactant A and reactant B. Reactant A is the box, reactant B is that darkened circle, okay? If we're trying to figure out the total number of collisions, and I only have one of each, they could only collide one time, okay? If you multiply the numbers you have of each, that's how you'll get the possible number of collisions. So like in the second box, 1 times 2 is 2, so I would have 2 collisions. This third box is 2 times 3, which is 6. And the last box is 3 times 4, which is 12. Okay, so the relationship between the number of particles and the number of collisions that you would have would be take the number of A times the number of B, and that will equal the number of collisions. So what this tells us is the number of collisions that you have should increase the reaction rate. So that means an increase in the number of A and an increase in the number of B should lead to an increase in the number of collisions, which should produce product faster. And that leads us to an increase in the rate of the reaction. So the rate is generally how quickly you produce product over time. So the rate of a chemical reaction is directly related to the product of the concentrations of the reactants. Okay. Now, anytime we've got a rate of a reaction that we're looking at, you can actually write an equation to represent the rate as it's related to the concentrations of reactants that are present. Generally speaking, the rate would look like this. This is known as a rate law. This is something that you dive into if you take AP Chemistry. And the rate law consists of a rate constant, K, which varies depending upon the type of reaction that we're looking at. And here we've got it being multiplied by the concentration of reactant A raised to some power times the concentration of reactant B raised to some power Y. X and Y are referred to as orders with respect to the concentration of A and B. Okay, so X and Y are known as orders. That means they could be values. They could be 0, 1, 2, 3, depending upon the situation. They will sometimes say the order with respect to reactant A is 1, which means X is 1, okay? They will also add X and Y together to get the order of a reaction. So if you add X and Y together, let's say they're each 1, that means the order of the reaction would be 2, okay? Now, let's take a look at the top of the next page. Everything that I just described to you is outlined within this paragraph. We talked about the rate law, the rate constant K, and the orders X and Y, okay? So let's come down to the quick check and take a look at this. So it says, write a general form for a rate law with 2 reactants C and D, assume the reaction is first order for each reactant. Okay, so that means the rate is equal to some rate constant K times the concentration of C and the concentration of D. Now, since X and Y, which are the orders or the exponents of each reactant, are 1, you could either include them or you could omit them, and it would be assumed that they're 1. Okay? Number 2, assume we have a reaction that occurs by this rate law. The rate equals K times the concentration of A. If we double A, what will happen to the rate? So that means it will look like this. The rate equals K times 2A. What do you think will happen to the rate?
Double.
Yeah, the rate doubles. Okay, so that means if you have A, that would make this equation look something like this. What would happen to the rate? Yeah, the rate halves. Okay. Take a look at number 3. Assume a gaseous reaction occurs by the rate law. The rate equals K times A times B. How would the rate be affected if the volume of the container were halved? Okay, if I halve the container, what happens to the concentration of A and B? If I make any container smaller, what happens to the concentration of something? If I make this room smaller, then I would, and I had like a concentration of 1 molar solution in it, okay? If I have this room, what happens to the concentration? Does it go up or down? It goes up, right? Because now we're occupying more volume. So that means the concentration of A did what? Increases by 2. And so does the concentration of B, right? Okay, so then they want to know what happens to the rate. Well, what's 2 times 2? 4. So the rate increases by 4. If I increase the temperature is going to make my reactants move faster, which means they will collide more often, which means they should produce product quicker. So what will happen to the rate if I increase the temperature? Will it go up or down?
It goes up.
It goes up. Okay, so if the rate goes up with increasing temperature, what part of the rate law is affected by temperature? You only have like 3 options, right? Okay. Okay, we're going to spend the rest of class talking about reactants colliding. It's not going to take us very long. When you have reactants colliding with each other, each collision is unique. They have their own energies, they have their own directions that they travel after they collide. It's sort of like playing pool. Okay, so if you take a look at the next page, they give you an image of what this looks like. Okay, so think of the billiard balls as reactants colliding with each other. 3-dimensionally, the collisions look something like figure 2.3.3, right over here, okay? And generally speaking, we follow something called the collision theory. And the collision theory says that the rate at which you produce a product depends upon how many collisions you have over time between the reactants, and then how many of those collisions actually successfully produce product, and that depends upon a couple of things that I'm going to tell you in a little while. Okay, so let's take a look at the next page. Don't assume that all collisions have enough kinetic energy to react. The minimum kinetic energy that reactants have to have when they collide is known as the activation energy, which we saw in the graph, right, in the previous section. So only collisions between reactants that have enough kinetic energy to obtain or attain the activation energy will actually be able to break bonds between themselves and then form bonds in products and result in a chemical reaction. Anytime you're dealing with gases, gases usually have high activation energies. So a lot of those reactions actually don't happen at room temperature. They happen at much higher temperatures. And let's take a look at a graph that shows us what something like this looks like. So let's take a look at the next page. On the next page, they're showing you how the kinetic energy changes dramatically at different temperatures. So T1 is this curve right here. You can see how a lot of the collisions that occur do not have enough kinetic energy to react. And then the other curve is at T2, so this is a higher temperature. You can see the shift that we have. And we have a lot more particles with higher kinetic energies, which should result in more successful collisions, which means we should produce product faster. So in addition to meeting the activation energy, the way that the reactants collide has to be favorable in order for a successful collision to occur. So what does that mean? Let's take a look at this reaction here. When you have carbon monoxide colliding with nitrogen dioxide, ideally you're going to produce carbon dioxide and nitrogen monoxide gas. But they may not collide in such a way that allows them to produce the products that you want. So here we've got two scenarios. We've got collision 1 and we've got collision 2. In collision number 1, you're producing carbon dioxide and nitrogen monoxide. This is what you want. In order for this to happen, the carbon in carbon monoxide has to hit an oxygen and nitrogen dioxide. And it has to have the activation energy, meet the activation energy to produce product. Down here, when the carbon hits the nitrogen, we do not produce carbon dioxide and nitrogen monoxide. We don't produce anything new, actually. Okay, so this is showing you how the way that the reactants collide actually matters. Okay, let's take a look at the next page. We're going to stop there.